So we've been discussing continuous random variables. In particular, last time we finished the end of the lecture with exponential random variables. Today is the 15th. This is lecture number 18. Okay, so last time we talked about exponential. Random variables. Random variable. And we discussed quite a number of things. For example, we discussed the CDF. So if I have a function that is a random variable that's exponentially distributed, you know what? Right before we talk about the CDF, let's talk about the PDF first. So the PDF is a piecewise function, lambda e to negative lambda x. That's when x is greater than or equal to 0, and it's 0 otherwise. Right, that's the PDF, the probability density function. And then we discussed the cumulative distribution function, which looks like this. And let's call this f of t, just to change the variables a bit. And of course, there's nothing at negative infinity or to 0. So it's only defined, the PDF is only defined when x is bigger than 0. So even though this is the direct definition of a probability density function, we have to account for the fact that the PDF is given this in this form. And we saw we can integrate this, and we saw that this equals 1 minus e to the negative lambda x, right? So that's the cumulative distribution function. Okay, CDF. So we found the exponential function, the PDF, and the CDF. And we also talked about the expectation, or the expected value. And the expected value, we found that to be 1 over lambda. Right? That was our expected value, or our mean of our exponentially distributed random variable. And one thing we did not get to cover, which I want to cover now, is the variance. So what would be the variance? Oops. What would be the variance? So how would we compute the variance of this exponentially random variable? Anyone out there? A bit early, huh? A bit too early on a Monday morning for variance. But what would we Yeah, something like that. Yeah, that would be it. But instead of a plus, there's a minus, right? So it's originally this is the definition, right? This is x minus mu squared. That would be the expected value. It's the expected value of the squares of the difference between the random variable and its expected value, its mean. That's what the variance is. It's an expected value. You understand? So the variance is an expected value of this new random variable, which is the random variable that you're initially speaking of minus the expected value of that random variable squared. So when you do that and you expand things out, what you get is this is the expected value of x squared, of the random variable x squared, minus the expected value of x, and this entire thing is squared. So remember, mu and expected value are the same. So mu is equal to the expected value of x. We normally use mu to denote expected value. Okay, so the nice thing is we already computed one of them, the expected value of 1 over lambda. We already know that's 1 over lambda. So this will be 1 over lambda squared. But the question is, what is the expected value of x squared? So we have to go back to our definition of expected value of x squared. So again, what's the expected value of x squared? Well, we do the negative infinity of x squared this time times the probability density function. And then negative infinity to infinity. Well, there's nothing at negative infinity, right? The way f of x is defined, and x is defined as x has to be greater than or equal to 0. So from here to here, this is strictly the definition of just expected value of any random variable. But now when we're speaking about a random variable in particular that's exponentially distributed, this lower bound will become a 0. This will remain to be infinity, and we got x squared times, and then what's f of x? F of x is lambda e to the negative lambda x dx. So again, this here is f of x. Okay, we can take the lambda out because lambda is considered to be a constant in this integral. So we got from 0 to infinity of x squared e to the negative lambda x dx. So now the question becomes, how do we compute this integral? So you have to kind of remember how we computed the integral for e to expected value of x. So what do we do here? What's the technique that we have to apply here? Integration technique in particular. By parts, that's right. So then what would be the parts here? So u would be what? And what would dv or v prime, what would that be? So normally we consider x is, yeah, in particular, x is u. We can do x squared. Because with x squared, we get u prime, right? Which is 2x. And then how about v prime? This would be e to the negative lambda x. And taking the derivative of this would be simple as well. So what's the antiderivative of e to the negative lambda x? Anybody? Antiderivative of e to negative lambda x. So the reason why this is an easy one is because e is a very nice function, because normally the derivative of e to the x is itself. So the antiderivative of e to the x is itself, right? So yeah, we don't worry about the plus c so much in this case for the integration by parts. but this will be e to the negative lambda x divided by negative lambda. And now remember why that would be the case. If we differentiate this, we should get back to this original function. So we're undoing the chain rule because there's a negative lambda next to the x variable. So now lambda, and then you parentheses, you do uv, right? So this becomes x squared e to the negative lambda x over negative lambda. This is being defined from 0 to infinity minus, now the integral of 2x, this is u prime, times e to the negative lambda x over negative lambda dx, and this goes from 0 to infinity. Everyone with me so far? You can take out the negative lambda and the 2 out of this integral. And so we get lambda x squared e to the negative lambda x over negative lambda from 0 to infinity plus 2 over lambda x e to the negative lambda x 0 to infinity of dx. And let's just look at this a little bit here. This is going to infinity, so normally we consider this as a limit. So limit as x goes to infinity. So the upper bound of the integration here would be, this would be x squared e to the negative lambda x over negative lambda minus, and then you plug in 0. But when you plug in 0 to here, everything becomes just 0. So that goes away. So that's pretty nice. Now, what happens when x goes to infinity? Well, we can treat this here, this limit here, we can treat this as a case of L'Hopital's rule. If I place the e to the negative lambda x, I could put this in the denominator, e to the lambda x. Now, the reason why we can apply L'Hopital's rule is because if you notice, this goes to infinity as x goes to infinity, and this denominator goes to infinity as x goes to infinity. So you can actually apply L'Hopital's rule twice. You can differentiate the top and the bottom twice, and you realize that this also goes to 0. So this entire thing here just vanishes. This becomes 0. Okay? So then what we're left with is this lambda here on the outside being multiplied here, but the lambdas will cancel out. And I'm left with 2 integral from 0 to infinity of x e to the negative lambda x dx. Now, what do you notice about this integral? We can apply integration by parts one more time. So this is one of those situations where you apply the integration by parts twice, one after the other. But what do you notice about this particular integral at all? Anything? It's just like a random, like this is just, is there any striking similarities with another integral that we have done? Right. Thank you, Daisy. This is exactly the expected value of x, isn't it? Isn't this the way we define the expected value of x? As x times what? Well, we're missing the lambda here, right? Did I put the lambda? We're missing the lambda. So this is almost it, actually. So this should look like f of x. F of x is what? lambda e to the negative lambda x. Do you guys see how similar this is? All we're missing is a lambda, right? So this is what we're gonna do. We're gonna be a little tricky here. We're gonna say, hey, you know what? Let's make a lambda. Let's write this 2 over lambda times lambda. Do you see what I'm doing here? I'm being a little sneaky because then I can put the lambda inside the integral and I get 2 over lambda times integral from 0 to infinity of x times lambda e to the negative lambda dx. So now this is the expected value. This is the probability density function of an exponentially distributed random variable. And I already know what this is. I already know what this expected value is. What is the expected value? This equals the expected value of exponentially distributed random variable. And I already know what that is. We said that in the beginning. What was it? Wasn't it 1 over lambda? So then the expected value of x squared becomes what? 2 over lambda squared. So don't forget what we just figured out. We figured out the expected value of x squared. And we did all of this. All of this was done so that we can find what the variance of x is. And again, the variance of x is the expected value of x squared minus the expected value of x squared. So what's the expected value of x squared? We found it, 2 over lambda squared. What's the expected value of x? It's 1 over lambda. And if I squared it, I get 1 over lambda squared. So 2 over lambda squared minus 1 over lambda squared is 1 over lambda squared. So that's the variance of x. Did I lose anybody here in this, from here to here in this step where I just just magically multiply and divide by lambda? I did so because it was a convenience. It was an algebraic convenience that once I have this lambda constant here, I have the expected value integral definition of the exponentially distributed random variable, which I know what that number would be. It's 1 over lambda. Yeah, and especially when you do integration, there's a lot of this manipulation where you can just add so conveniently a number by adding, really you're adding by 0, or in this case you're multiplying by 1, right? I'm really just multiplying this entire thing by 1 because I'm multiplying it by lambda over lambda, which is equal to 1. But I do so because it just helps me. It conveniently helps me simplify my computation. Again, I could have just continued on my merry way and I still would have gotten 2 over lambda squared. I would have just had to do more integration by parts, but I want to just cut to the chase. Okay, so we discussed the PDF, the CDF, the expected value, and the variance. And these are all primary, you can think of them as primary characteristics for every random variable we've discussed, whether they be discrete or continuous. You should always be able to, given the name of a random variable, given the type and name of random variable, you should be able to identify its PDF, its CDF, which are connected automatically, and then the expected value and the variance. So those 4 things are primary characteristics of every random variable. Okay. So one more thing I want to talk about in terms of the exponential random variable is something in particular to this random variable, which is called the memorylessness property. of exponential random variables. So something very special, and particularly for exponential random variables, is this idea of its memorylessness. That's a good word. Memorylessness. What am I saying? What I'm saying is that with the exponential random variable, when some random variable is exponentially distributed, uh, there's something about it. So before that, recall the use of exponential random variables. Exponential random variables are used for several things. So examples are used for the following examples. So, for example, the amount of time until an earthquake occurs. The amount of time, so keyword is amount of time. So a lot of time dependent scenarios. So the amount of time, until a phone call that a phone call comes from a wrong number. Yeah. So things where even until the amount of time until the war breaks out. So as you can tell, the idea of continuity is embedded in the element of time that we have. Time is not something you can like take, even though I guess you can think of it as taking photos probably is the best way where we can capture, quote unquote, an instant of time. But in reality, we can't. We can't tangibly take a second out of time. So you see the difference between discrete and continuous things. Like for example, sand is discrete. You can take a there's an even though it's very fine, you can get to the one element of having one grain of sand, which is possible, but you can't take one element of time, for example. It's not tangible. So that's something that just continues and flows. So oftentimes time, as you can see here, time is normally something we can use that we model with random variables, and particularly continuous random variables. And if you notice the kind of scenarios that the exponential random variable models are things that occur after a certain period of time. So it's like the first occurrence of an earthquake after a certain period of time that's exponentially distributed in general. Until you get a wrong number being calling your phone, that the time that it takes for that to happen, exponentially distributed, so on and so forth, right? Does anybody see any similarity between exponentially distributed random variables and another discrete random variable that we spoke of? So for example, the binomial random variable, right? When we saw the PMF, how symmetric it was. And as we have more and more larger n, we get a very nice description of something that looks continuous, like the normal random variable. So what would be like its cousin? Right. The geometric, right? What was a geometric random variable? What did that describe? It described the first occurrence of success, right? For the first success, right? And but this was discrete world. So we had certain tries until we got our first success. And for each one of those number of tries, there's a probability mass function. So the continuous version of it is the exponentially random variable. And if you also remember, the expected value of the geometric is 1 over p. The expected value of our exponential random variable is 1 over lambda. So there are some similarities, even the expected value version of it. But the difference is something called memorylessness. So what am I saying with that? So the idea is this. If I want to, so let x be exponentially distributed. Okay. So let's see if I want to find the probability that my x is bigger than s plus t. I should say given that x is bigger than t. Now, what does this mean? I want to know what's the probability that my random variable is bigger than this number, right? Given that it's already bigger than this number, t. So s plus t, and this is t. So this is conditional probability. How do we do conditional probability? Well, how is it defined? It's defined as a probability that we have x bigger than s plus t divided by the probability that x is bigger than t. Now, what is probability that x is bigger than t? Isn't this 1 minus the probability that x is less than or equal to t? Right? Complementary counting. But then isn't this the CDF, the cumulative distribution function of x? And don't we know what that is already? 1 minus e to the lambda t. But when you do this, what do you get? You get e to the lambda t. I think, and this is negative, right? Yeah, this is a negative. Forgot the negative. There's a negative here. So the probability that the x value is bigger than t is e to the negative lambda t. So then I can write this in the denominator as e to the negative lambda t. Now, what's going to be the numerator going to look like? Well, it's going to be so this is the denominator. What is the numerator going to look like? The probability that x is bigger than s plus t. That's equal to 1 minus the probability. Same idea. X is less than s plus t, which this is equal to e to the negative lambda of s plus t. But this is equal to e to the negative lambda s plus lambda t subtracted, pardon me. If you distribute the negative lambda, right, this is lambda t, you can write this as e to the negative lambda s times e to the negative lambda t. So the top part here will be e to the negative lambda s times e to the negative lambda t. But what happens? There's cancellation involved, right? We get e to the negative lambda s. But e to the negative lambda s, what is this? Isn't this the probability that x is bigger than s? But we found what? The probability that x bigger than s plus t, given that x is bigger than t. Now, mathematically speaking, this is called memorylessness. This is mathematical, the memorylessness property. So why is it called memorylessness? Because in a sense, we forget. It becomes irrelevant that this is true. X is bigger than t. So suppose X is one of these three scenarios. Let's say the T represents the amount of time that war breaks out. So suppose the war will break out more than 100 years from now. Given the fact that there has already been 200 years. So suppose this is 200, right? Suppose there hasn't been any war after more than 200 years. And then I want to see what's the probability that war will be there won't be any war in 300 years, given the fact that there has been any war for the past 200 years. Do you guys follow me? Well, that probability is equivalent to saying what's the probability that war will be more than 100 years from now. Do you guys see that? We're saying the probability that the war will happen 300 years, that there is no war until after 300 years, given the fact that there has been any war in 200 years. That's equivalent to saying what's the probability that the war will occur 100 years or more than 100 years from now. So the idea that there hasn't been any war in the past 200 years is almost not accounted for. We forget that that even happened. That's the idea of memorylessness. That's the idea behind the exponentially random variables. If you start from this point on, whatever happened before, it doesn't affect the distribution of the time. It's the same if we start from now. Then what makes the amount of time exponential if you're not taking into account whatever happened before? No, it's not that we're not taking into account. It's just that by the nature of this random variable, right, it's given by the exponential function lambda e to the negative lambda x. And x is, in this case, the amount of time until something occurs. The very structure of that PDF causes this idea of memorylessness. So if we want to figure out the amount of time that something happens, given that our time has already elapsed, that distribution is the same as if we just started from today and this moment on forward. It doesn't change. That's the weird, I would say, the strange part or characteristic of exponentially random variables. Yeah, it's something in particular to this random variable. It's this idea of memorylessness. And it follows from just like I said, the structure behind it, because mathematically speaking, these exponential functions in terms of t, they just disappear. So what we started with, caring about whatever t happened, right? Whatever t was, eventually actually didn't really matter. It becomes an irrelevant piece of information, and we only care about what happens at this moment in time. So this is given the fact that time has already t amount of time has elapsed, and I want to find what this would be. But what this is showing you is that whatever happened up until that point, kind of we forget about it, quote unquote, and we just start from this moment on. So that's what exponentially distributed random variables really indicate. They indicate that we start from this moment on. It doesn't matter what happened before. We start from this moment onward. Okay, so that's a very interesting aspect of exponentially distributed random variables. Okay. So can you scroll up? Yes, of course. Mm-hmm. Okay. So let me give you one example of this, and then we can move on to joint distributions of random variables. Okay, so let's look at an example. So the time in minutes between arrivals of customers to a post office. So you see how we've also had a random variable in the past discussing things about entering a post office. I don't know if you guys remember what that was. Do you guys remember? So remember Poisson? Poisson was like the number of customers within a time frame. So the number of people that enter a post office within an hour or something. But now we're not considering the number of customers, we're considering the time it takes for a customer to arrive. So that's exponentially distributed. The number of customers entering a store within a time frame, that's Poisson. So I just wanted to make that connection there. So okay, so the time between arrivals of customers to a post office is to be modeled by a exponentially by the exponential distribution with mean 0.43. So part A, what is the probability that the time between consecutive customers is less than 15 seconds. So in a sense, this is where the memorylessness property comes into play. We assume in a sense that we're starting from right now, and right now indicates that a person already came, right? A customer has entered the post office. And now we want to figure out how long does it take? What's the probability that the next one will appear? Next one will arrive. So then X here is what? X is the time, right? Until customer arrives. Now, I want to find the probability that X is less than 15, which means I want to do the integral from 0 to to 15 of um, lambda e to the negative lambda x dx. But what am I given? Do I know what lambda is? Yes, I know the expected value. I know the expected value of x, which is 0 0.43, but this is equal to 1 over lambda. So what is lambda? Lambda will be 1 over, right? 1 over 0.43. And if you put that in your calculator, 1 over 0.43, is some weird number. So I'm going to leave it as lambda for now, okay? Now, what is this? Didn't we know what this the CDF, this is a CDF. Didn't we discuss what the CDF was? It was 1 minus e to the negative lambda times 15, whatever the a what the value was here. And now lambda is what again? Is e to the negative 1 over 0.43 times 15. Put this in your calculator to compute this. And what do you get? Does anybody get it? So yeah, I don't think your calculator, at least not the TI-84, it doesn't have the exponentially distributed random variable stuff. So we have to do 1 minus e to the negative. I'm gonna put the the fraction 1 over 0.43 times 15. And I get 1. Now that's strange. Hold on 1 sec. It's very strange that we get such a tiny oh, do you guys see the tiny mistake that's done here? Does anybody see the mistake that's done here? No. Parentheses, no. It's not. I typed in everything correctly. It's just that I used one wrong number. And it doesn't have to do with the parentheses here in the calculator. It has to do with the parentheses in the question itself. So in the question it says the time in what? The time in minutes, right? X is the time in minutes. But the question itself, part A says, what is the probability at the time is less than 15 seconds? So the X value in the one you see in the calculator shouldn't be 15 because that would indicate 15 minutes. So that's something I just realized myself. So instead of writing this, I should write what? Just make this a 15 over 60, right? Which is 0.25, right? So it should be 0.25 instead. And now I feel much better about life because I was gonna lose my mind. Because things like this happen all the time. You gloss over one little thing and you think you know you want to reevaluate your whole life up until that moment, and then you think you get things right and you apply the memorylessness property that nothing ever bad happened at all. Anyways, so the answer is 0.44088, blah, 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 which is approximately 0.44 if you want to round it to nearest two decimal places. So that is the answer here. So I hope you guys are starting to get more comfortable with finding probabilities of these kind as you start to see that the setup is very similar to every other question that deals with the probability of something happening or probability of an event. When you use the CDF function, right, you use the integral. The only thing that changes is the actual PDF itself. So in this case, we're dealing with the PDF of an exponential random variable. And so just to finish this example off, what's the probability? So given that the time between consecutive customers is greater than 10 seconds, what is the chance that it is greater than 15 seconds? So if you notice, this is all immediately a conditional probability question, correct? And hopefully you see in this example what memorylessness in dealing with exponential random variables really means. So I'm saying, suppose that the time it takes for consecutive customers to arrive is greater than 10 seconds. What is the probability that it is actually greater than 15 seconds? So this looks very similar to what we had with the S and the T stuff, right? We're saying that X will be what? What is the probability that it's greater than 15 given that it is already greater than 10? And if I rewrite this, this kind of looks like this. What's the probability that X is bigger than 5 plus 10 given that X is greater than 10? So for example, given that 10 seconds have already elapsed, right, between the first and second customer arriving, what's the probability that the time that it takes for the next customer to arrive will be bigger than 15, given the fact that 10 seconds have already elapsed? Do you see? And then we say, well, it's the same. That probability that you're looking for is the same as if we were to start right now and say, what is the probability that the next customer will arrive in more than 5 seconds from now? So the event, the scenario of having the next customer arrive after 15 seconds, given that 10 seconds have already elapsed, is the same if I were to ask, what's the probability that the next customer will arrive after 5 seconds? Do you guys see that? So this here is equal to the probability that x is bigger than 5 by the memorylessness property of memoryless property. Yeah, it makes more sense when you have a concrete example. So I showed you the theory, and now it's kind of backed up by a concrete example. So this is going to be e to the negative lambda times 5. Well, be careful because 5 is seconds. All this is seconds, and our the way our random variable is defined is by minutes. So 5 seconds is not the right entry here. It should be what? 5 over 60, which is a 12th of a minute. So what happens when we have e to the negative lambda times 1/12? But lambda was again what? 1 over 0.43 times 1/12. So you put that in your calculator, and what do you get? E to the negative 1 over 0.43 times 1 over 12. And I get 0.82. 0.8238 dot 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 dot. Okay. Everyone follow this? Everyone follow the memoryless property and how it's applied here. Any questions? Any concerns? Okay, so we can finish with exponential function random variables here. So there are many more continuous random variables, but these are the main ones that we'll consider for now. Don't you have to subtract by 1? No. Because the probability of x being bigger than 5 is equal to 1 minus the probability x is less than 5. And we know this. This is a CDF. This is 1 minus e to the negative lambda times 5 over 12. But this is 1 minus that. So this will equal e to the negative lambda times 5 over 12. So be careful. This less than symbol, greater than symbol matters. The less than symbol, this indicates cumulative distribution function. So we start from negative infinity, or in this case 0, and we go all the way to 5. But this is saying the opposite. It goes from 5 to infinity. That's not cumulative. That's not the way cumulative distribution function is defined. Okay. Okay. So, yeah, given the time constraint here, we may not go over everything. But that's okay. The first thing that I want to discuss is understanding the distribution of a function of a random variable. So far we've been just dealing with random variables, like just straightforward, very simple examples of random variables. We've discussed discrete random variables, Bernoulli, binomial, Poisson, geometric. And then we've discussed continuous random variables, uniform, normal, exponential. random variables, right? So we know the different types, the different names, and everything related to them. Now the question is, what if we do functions of those random variables? Which we've seen already a little bit of, right? So for example, when we compute the expected value of x squared, x is a random variable, and x squared is a function of a random variable, which is taking the random variable x and squaring it. So the idea is now what happens when we have more complicated functions of simpler random variables that we've discussed. How can I find the distribution of that new random variable, which is a function of those random variables? So what is the idea? So the idea is that let's say this. Let x be a continuous random variable. So this is for particularly for continuous, okay? Having a probability density function, so a PDF, and we're going to define it now. Now we're going to be a bit more specific with defining our probability density functions. So this subscript x is indicating this is the PDF of the random variable x. Okay, now we're going to have to be able to do that now, because now we're going to be considering the probability density function of different functions, not just x, maybe y, maybe z, maybe u, maybe v. There's going to be many more letters now. Okay. Okay, so this is one thing. Suppose that g of x is strictly increasing or decreasing. So it's an increasing or decreasing function, differentiable and differentiable, I should say. Then the random variable y defined by some function g of x has a probability density function so this is f of y of little y is equal to f of x g inverse of y multiplied by the derivative, the absolute value of d dy g inverse of y. This looks crazy, but with some examples, hopefully it starts to make sense. So that's if y does not equal g of x. And this is if y equals g of x for some x, for all x. This looks strange. It does. Okay, so how do we see this in a real life example? Okay, so let x be uniformly distributed over 0, 1, and let y be equal to x to the n. You know what? Let's call this x cubed for now. And let y equals x cubed. For y. So for y between 0 and 1, I want to find what f of y is. I want to find the distribution of y. I know everything about x, don't I? Uniform distribution over the interval 0, 1. I know everything about it. We've talked about uniform random variables, but now take this uniform random variable and cube it and say, you know what, call that a new random variable. Let's call that y. Now this random variable y is based upon a uniform distribution, a uniform random variable called x. And now I want to understand, how does the distribution of y work, given the fact that it comes from a distribution that's called uniformly distributed. And instead of taking just x, I'm cubing x. So how does that change it? What does it look like now? So what we do is we take it step by step. We take the probability that my new random variable y is less than or equal to y, right? That's the definition. And then what we do is we do some algebra within the parentheses. That's what's going to happen. We're going to be doing some algebra inside. So this is equal to the probability that x cubed is less than or equal to y. And then I don't want x cubed. I want to know what x is by itself. So what we're doing is we're going from what we don't know and we're going back to something that we do know. So we don't know how to deal with y because it's something new. And we don't know how to deal with x cubed. But we do know how to deal with x. So how do we get rid of this cubed? What do I do on both sides? I cube it, cube root it. So this becomes x is going to be less than or equal to the cube root of y. Does everybody follow me? So the probability of this is the same thing as the probability of this. But what was x again? X was uniformly distributed over 0, 1. So this becomes the CDF. What does this become? The CDF of x. And x is what? Uniformly distributed from 0 to 1. If you guys remember, how do we do this? This is the integral from negative infinity to x of f of x dx. In particular, this is of the PDF of x. But what's the PDF of a random variable from 0 to 1? If you guys remember, it's just 1. This equals 1. That's very easy. And now, of course, this x value is not, this x value here, this upper bound comes from this guy. So this is the cube root of y. And again, this negative infinity becomes 0 because the uniform distribution only goes from 0 to 1. So this is 0 to the cube root of y of 1 dx. But this is like saying find the area of the constant function 1 between 0 and the cube root of y. And the area of a rectangle where one of the dimensions is 1 and the other one is the cube root of y is just the cube root of y. So what did I just figure out? I figured out that the probability density function of y less than or equal to y, because the random variable y is the cube of the uniform random variable x, this is equal to the cube root of y. Does everyone see that? This is the CDF of y. Any questions about this? Of course. No. The CDF will always be different because the PDF will always be different because the random variables that we're starting from will always be different. This example is a specific random variable. It's uniformly distributed over one. That's very specific. So in y, this new function y is this random variable y is a function of the uniform distribute this of the uniform random variable x. I'm cubing it. In cubing the uniform random variable x, now I have this new random variable. Do you understand? I got a random variable x, which is uniformly distributed over one, and then I did something to it. I cubed it. In the act of cubing it, I created a new random variable. It's x cubed. It's random variable, the uniform random variable, distributed random variable from 0 to 1. Now I'm cubing it. Now my question is, what does that mean? What does that look like? So then that's when we try to study. No, this is a good question. It's a great question. Because when you look at it, it does look like what's going on. So it's going to change for depending upon every random variable that you start with. So I started with the uniform random variable, I cubed it, and now I have a new random variable. I want to know more about it. How do I learn more about a random variable? Well, I have to learn more about the CDF and the PDF. Will this subject be on the exam? It may be. Definitely may be. It's on the homework. And I have to alter the homework a bit because we didn't cover everything. So you'll see less problems on the homework for this homework assignment. So the CDF of y, of this new random variable y, is the cube root of y. So if I want to find, and of course this y though has to be between 0 and 1. So if, for example, if I want to find a probability that my y random variable is less or equal to 1/2, then that's going to equal to the cube root of 1/2. Okay. And then the question that follows from this is, what's the PDF? What would be the PDF? What's the PDF of y? How do you find the PDF of y? Well, go back to what's the CDF? The CDF of y is the probability that y is greater to y, right? Which is equal to, and the definition is from negative infinity to y of f of x, for example, dx, right? That's the definition, correct? But how do I get y? How do I get the function here? Just this function. How would I get rid of this integral sign? What operator would I have to apply to this, both sides of the equation, to get rid of that integration sign? What would I have to do? This is just fundamental theorem of calculus. What is the inverse operator of integration? Derivative. So to find the PDF, if I know the CDF, I just have to differentiate. So do you see that? So the probability density function becomes the CDF. This becomes the PDF when I differentiate. That's how they're related, right? Normally, what would he say, what we start with? We start with the PDF, integrate, you get the CDF. Well, if I had the CDF, how do I get the PDF? Differentiate. So then the the um the derivative of the random variable y with respect to y is equal to the derivative with respect to y of the CDF, which happens to be the cube root of y, which is the derivative of y to the 1/3, which is equal to 1/3, right? Times y, and then you subtract by 1, you get negative 2/3 y. So the PDF of y is 1/3 y to the negative 2/3.